of vibrations of stretched string clamped at both ends. Now let us take a string which is clamped at or fixed at both ends. When we plug the string, a transverse wave travels along this string. Let this be the incident wave. When it reaches this end reflects back this wave, okay, and this is the reflected wave, okay. In such a way, these two waves travel in opposite direction to each other and produce stationary waves. As this is clamped at both ends, we find node position, which is nothing but zero displacement position at both ends, and anti-node position, which is nothing but maximum displacement positions, which is founded in the middle part, right? Now let us discuss about modes of vibration. So for that, let the displacement of incident wave be yi, and such displacement is written as, if A is the amplitude of the incident wave, then A e to the power of j omega t minus x by v. Similarly, if yr is the displacement of reflected wave and b is its amplitude, then it is written as yr equal to b of e to the power of j omega t of minus x by v. Since here displacement is in opposite direction to the incident wave, right? So it becomes b e to the power of j omega t plus x by v. Using superposition principle, the resultant displacement is written as y equal to yi plus yr, where yi is e to the power of a e to the power of j omega t minus x by v, yr is b e to the power of j omega t plus x by v, right? Now as this is clamped at both ends, let us write the boundary conditions for this string, okay. Let L is the length of the string, okay. So at both boundaries, one side x will be 0, other side the length of the string we are saying as L. As at both ends we clamped or fixed the string, the displacement at this end will be 0 and the displacement at this end will also be equal to 0. Now in this equation in equation 1. Let us take it as equation 1. Let us apply first boundary condition in equation 1. Now first boundary condition is at x is equal to 0, y equal to 0. So the equation 1 is y equal to a e to the power of j omega t minus x by v plus b e to the power of j omega t plus x by v. Now y equal to 0, we are substituting a e to the power of j omega t since x is equal to 0 plus b e to the power of j omega t since x is equal to 0. So it becomes a plus b of, we are taking e to the power of j omega t as common. As this is the exponential term, it cannot be equal to 0. So a plus b must be equal to 0. So we get a equal to minus b. Now substituting this a equal to minus b in equation 1, in place of b, I will substitute minus a. Now the equation turns to be y equal to a e to the power of j omega t minus x by v minus, in place of b I am substituting minus a, e to the power of j omega t plus x by v, right? And now in these both equations, if we see, e to the power of j omega t is common and a is common. Now taking a and e to the power of j omega t as common, we get here e to the power of minus is there, minus j omega x by v minus e to the power of j omega x by v. Now let us use the relation e to the power of minus j theta minus e to the power of j theta. So the value of e to the power of minus j theta is cos theta minus j sin theta minus cos theta plus j sin theta. Now this becomes cos theta minus j sin theta minus cos theta minus j sin theta. Cos theta strikes off. Now we get minus 2j sin theta, right? Here in above equation, in place of theta, we are having omega x by v. So now e to the power of minus j omega x by v minus e to the power of j omega x by v becomes minus 2j sin omega x by v. Now substituting these in the above equation, we get y equal to a e to the power of j omega t minus 2j sin omega x by v. Now let us apply the second boundary condition in the above equation. Second boundary condition is at x is equal to 0, y equal to L, at x is equal to L, y equal to 0. Now substituting y equal to 0, a e to the power of j omega t minus 2j sin omega L by v. In place of x we substituted L, right? And now here a and exponential term cannot be equal to 0. So the term in the bracket 2j sin omega L by v must be equal to 0. As j is not equal to 0, we write sin omega L by v equal to 0 or sin omega L by v equal to sin n pi, or omega L by V is equal to n pi, right? Or omega equal to n pi V by L, right? Now we know that omega means 2 pi nu, where nu is the frequency, n pi V by L, pi strikes off, nu equal to n V by 2L. Now for nth mode, we can write this equation as nu n is equal to nv by 2L. But we know that velocity of transverse waves in strings is under root T by mu. So for nth mode, the frequency value is n by 2L under root T by mu, right? This is the frequency of nth mode of vibration of transverse waves, Now in first case, incident wave, reflected wave, two nodes are formed at the fixed end and antinode in the middle part. Now only one loop is formed. This we call it as fundamental frequency, or we can also call it as first harmonic, right? So for this n equal to 1, so nu 1 becomes 1 by 2L by under root T by mu. Similarly, if two loops are formed, these are node positions, antinode position, so nu 2 equal to 2 by 2L under root T by mu. This we call it as second harmonic or first overtone, right? In similar way, if we have 3 loops, okay, if we have 3 loops, node positions, antinode positions, we get nu 3 equal to 3 by 2L under root T by mu. We call it as third harmonic or second overtone. In such a way, we can write the number of modes of vibrations in such a way, and now we will get the first, second, so on harmonics or overtones, and the fundamental frequency comes out to be nu equal to 1 by 2L under root T by mu. So this is about the modes of vibrations when string is clamped at both ends.